Hello, my amazing students. This is Mrs. A, and we're going to talk about 6.1, which is the exponent rule. So here are some examples of the product rule, which is what we're going to go over first. And remember, the product rule simply states that if you have a to the r times a to the s, in other words, you have the same base with exponents, then the product, because they're the same base, is going to be a to the r plus s. Okay, so we add the exponents together when we multiply like bases. So here we're multiplying 5 squared times 5, and we know that 5 is also 5 to the 1 power. So now when we multiply these, we're going to add their exponents because we have a base of 5. We'll get 5 cubed, and 5 cubed was one of those I asked you to memorize, is 125. We would always go ahead and write that out. So now we have y's as our base, and because we have a common base, we're multiplying them together, and we're going to get y to the 13. On the next one, we've got coefficients and variables with exponents. We're multiplying them together because of the commutative property of multiplication. That means that multiplication can be switched around in any order we prefer. We can multiply the 4 and the 10 to get 40, and then we can multiply the two like bases together, the two x's, and then add their exponents and get x to the 13. The next one, we've got d times d to the 7 times d to the 4th. We can remember that d is d to the 1, and then when I multiply the like bases together, I will add their exponents and get d to the 12th. Down here, I'm kind of dead in the water because I have an x and a y. I cannot do anything to simplify that expression. All right, so then we have this a little bit more complicated problem here, where I have r's and t's and a constant in the front. So I'm going to use my commutative property, which tells me that I can multiply these together and get negative 21. I'm going to multiply my r's together, and that is r to the 1, which is going to give me r to the 5 and t to the 11th power. And we'll come back in a minute with some more exponent rules. Okay, so now we're going to discuss the basic power rule and the power of a product rule. So the basic power rule tells you, I call it the power to a power, but it tells you that when you have a power, a base raised to a power, and then you're raising the whole thing to another power, that then you multiply the powers. So this becomes 7 to the 12th, okay, and m to the 10th. Now here I'm raising a product to a power, so that's going to be 4 cubed x cubed. I end up raising both parts of the product to the power, and 4 cubed is another one that you should memorize, and that's 4 times 4 times 4, which is 64, and then we're going to tack on the x cubed. And then the last one is also a product raised to a power, so each part of the product will get the power, and we'll have 2 to the 5th and w to the 4th, also to the 5th, which is going to be 2 to the 5th is 32, and w to the 20. All right, so that's the product, the power rule, and the power of a product rule. The next thing is the power of a quotient rule. So when we're dividing, we have a quotient raised to a power, then just like each part of the product got a power, each part of the quotient will get a power, and we will get 4 cubed over 5 cubed, which 4 cubed is 64, and 5 cubed is 125. Remember, 5 cubed is 5 times 5 times 5. Now, here, this is a real combo because it's a quotient, but inside the quotient is also a product. So we're going to wind up having a negative 3a cubed over a b to the 8th cubed. So we're kind of throwing all of our rules together here. And then we have a negative 3 cubed, which is a negative times a negative times a negative will give me a negative 27. And then an a cubed. And then on the bottom, I've got a power raised to another power, so that's going to be a b to the 24. And when I get to that point, there's nothing more that I can do to simplify that one. So here are some power of the quotient examples. Then we're moving into some kind of mixture problems where there's a little bit more to it than that. So here we have 2 products raised to a power, and the 2 powers are different. So we're going to end up having to say, okay, well, that's going to be 4 squared f squared 2 cubed f cubed. Okay, so because of the commutative property of multiplication, which says I can multiply in any order I please, I'm going to make the 4 squared a 16, and I'm going to join it by multiplication with the 2 cubed, which is 8, and we'll work that out in a minute. And then the f squared times the f to the 3. Now I'm multiplying 2 like bases, so this is where I add the exponents. So I get an f to the 5, and 16 times 8 here is going to be 48, carry the 4, 128. So I wind up with 128 f to the 5. And then on this one down here, I have a quotient, but that quotient also has products in each part. That's a 10 down there. All right, so now I'm going to wind up with the numerator being raised to the 2nd power. So I'm going to get 12 squared y cubed squared. And then on the bottom, I'm going to get 4 cubed z to the 10 cubed. And then 12 squared is 144. And y, I'm not going to put that in parentheses, y to the 6, because I'm raising a power to a power I multiply. 4 cubed is 64 again. And z, that was 10 and 3, so that's 30, z to the 30. Now, the y and the z cannot combine in any way. So now all I have to do is take and reduce the 144 over 64, which turns into 9/4, and then the y to the 6th and the z to the 30 just get tacked on there. So we need to reduce the fraction, but we can't do anything with the y and the z. So that's just a little bit of an example of some combination problems. All right, so here we have some more combination problems that throw several of our rules in there, and even a little order of operations rule. So here our order of operations is peeking in here. Remember, order of operations, please excuse my dear Aunt Sally, and please stands for parentheses, brackets, braces, absolute values. Please excuse, the E stands for exponents and roots. And then my dear Aunt Sally stands for multiplication and division are on the same level, and then addition and subtraction are on the same level. So when we come up here, we have a parenthesis, we have the exponent. This little guy gets done last. The -3 in the front is going to get done last because we have to get this whole parenthesis taken care of. In order to get the parenthesis taken care of, we have to first take care of this, okay? So then it's 3 times, -3 times parenthesis squared. So we're going to take the parenthesis squared, operate on that first, and then multiply by a -3. The same thing down here. We're going to take care of the parenthesis, square it, and then multiply that result by 2. So here we go. We're going to take each part. 4 squared, A squared, squared, B cubed, squared, and then out here I'm going to put a -3. 4 squared is 16 times, since that's the only number we have, times -3 is -48. A to the 4th, because I'm raising a power to a power, B to the 6th. And that is the end of that problem. And then down here, we're going to take everything and raise it to the 2nd power. So 3 squared, y squared, n squared times 2. Okay, so 3 squared is 9 times 2 is 18. Y squared, n squared. Now, because I have a y and an n, I can't do anything. Because I have an a and a b, I can't go any further there. So now we'll come back with some more rules about raising something to a 0 power and to a negative power. Okay, so now we're talking about 0 exponents, and we'll talk about more later why this is true. But 3 to the 0, any base raised to the 0 power is 1. Okay, so it doesn't matter how complicated the product or whatever's in the parenthesis is, it's still going to be 1. As long as it's in a parenthesis and it has a 0 on the outside, it is 1. If we have a -4 raised to the 0 power, it is 1. Here we have a -6, but only the 6 is raised by the 0 power. Remember, an exponent only applies to the number or the variable directly preceding it. So only the 6 receives the 0 exponent. So this becomes the same thing as -1 times 6 to the 0, which is -1 times 1. That 6 to the 0 becomes a 1. -1 times 1 is -1. So those are some 0 exponent examples. And here's one more that a lot of people will miss, because 2/3 to the 0 is 1, and 3/2 to the 0 is also 1. But 1 plus 1 is 2, not 1. Okay, so now we're going to work on some negative exponents. All right, so here we go with negative exponents. Negative exponents have nothing to do with the sign of the expression. They have everything to do with the position of the number. So basically our rule for negative exponents is saying that if we have, here we got a little space, if we have a to the -1 it is the same thing as 1 over a to the positive 1. In other words, I have to send it downstairs. So if we make this an a to the r, then we get 1 over a to the r. Likewise, if I happen to have a negative exponent down below in the denominator, I would send it upstairs. So it doesn't matter whether it is already downstairs or upstairs, we have to send it the other direction. Okay, so let's look at some of these. These start out pretty simply and then they're going to get more complicated. So we have 3 to the negative 3, which means that I'm going to put 1 on the top and 3 to the positive 3 on the bottom. So I send it downstairs. Always send it across the division sign. If it's already up, I send it down. If it's down, I send it up. Okay, so we need to get it to a positive exponent. So 3 cubed is 27. So the answer is 1 over 27. On this one, I have another rule that I'm going to use. Basically, I can do this one 2 ways. The 4 to the negative 3 is going to have to go downstairs. The 5 to the negative 3 is going to have to go upstairs. To help this situation, I can turn both of them over. Since this one's going to have to go down, this one's going to have to go up, I can turn them both over and get 5/4 to the positive 3. And that means I'm going to have 5 cubed, which is 125, over 4 cubed, which is 64. On the next one, I've got a 1/3 to the negative 2, which means that 3 that's in the denominator has to come up. Now, it's a 3 over 1, but a 3 over 1 squared is the same thing as just a 3 squared, so the answer is 9. Now I have a negative number raised to the negative 2. Now remember that negative 2 exponent has nothing to do with the sign of the number. So I'm going to just keep the sign together and put the negative 2 on the bottom. And now the negative 2 has a positive exponent because that moving it changes from negative to positive. And now I've got 1 over negative 2 times negative 2 is positive 4. So that's one set of examples for negative exponents. So now, another page, we're going to take the negative and pull it off to the front because it's negative 1 times. 3 is the only thing that's raised to the negative 2 power. So the 3 is going to become a 1/3 to the 2nd power. And the negative 1 is out in the front. So the negative 1 is not affected. Remember, the exponent only affects the number or the variable directly preceding it. So 1/3 squared is 1/9 times negative 1 is negative 1/9. I can't write it down. That's negative 1/9 there. Okay, we got an n to the negative 8, which is going to be 1 over n to the 8th, which I don't need to put in parentheses. That was a boo-boo. 1 over n to the 8th. And then, since this is a quotient, and the parenthesis means that everything is raised to the negative 5 power, I'm going to take care of both at the same time by flipping the whole thing over and get m over 2 to the 5th, the positive 5, which means I'm going to get m to the 5 over 2 to the 5, and 2 to the 5 is 32. The last one is only the y has the -2 exponent. The 7 will stay in the numerator. The y will go to the denominator with a square. So there's that board of explanation examples. So now I'll take our little rule off of here. And now we have some more to do. So here we have two things that are going to have to move. The f is going to have to move because it has a negative exponent, and the g is going to have to move. And so I'm going to do them both. The f goes downstairs, and f to the 1 is just f. And the g to the 5 goes upstairs, and that's my answer. This next one here, the 9 has nothing that's going to go with it. The t to the 4 is just fine where it is and cannot be simplified. The only thing that can be simplified is an s to the -10 needs to move downstairs. So the answer is 9 over t to the 4 s to the 10. And the last one, we cannot combine the c and the d. They both need to change positions and move downstairs. So we're going to have 1 over c squared d to the 7. And we have one more board before we pause and put some more problems on here. Okay, so now this one has some negative exponents, it has some positive exponents, and it has a fraction. Okay, now the fraction cannot be simplified, so the final answer will still have 7/10 in it. Okay, the x cubed has no other x's to combine with, so we're going to leave the x cubed upstairs because it has a positive exponent. The z to the -4 needs to move upstairs to become a z to the 4. And the y to the -8 needs to go downstairs to become a y to the +8 on the denominator. And this one has a quotient raised to a negative, so we're going to completely rewrite the whole fraction and raise to the positive. So I flipped the whole thing over, raised it to the positive power, and so now I have 4 cubed c cubed over a cubed b cubed. The only thing that I can do there is simplify the 4 cubed and make it a 64. So that is the final answer there. So we'll come back with some more, a little bit more complicated combination type problems in a minute. Okay, the last thing in this video, which is still 6.1, is the quotient rule for exponents, which remember we talked about before. When we multiply like bases, we add the exponents. So it only makes sense that when we divide like bases that we subtract the exponents. 12 take away 8 is 4. So we know that multiplication and division undo each other. Okay, so when we multiply, we add the exponents. If I take this one and divide it by this one, I should wind up with that one, and I do. Okay, so if you were to expand this, remember, you would have 2, 2, 2, 2, 2, 2, 2, 2, 2, 2, 2, 2. We'd have 12 2's on the top, and we would have 8 2's on the bottom. I know this is going to look a little weird because I ran out of room, but 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. And we'd wind up with 2 times 2 times 2 times 2, or 4 2's left over. So it's kind of a weird picture. But let's start using this. So we have the same base, so we subtract the exponent, so we get 5 squared, And we know that 5 squared is the same thing as 25. We should simplify that. And then d to the 10 over d to the 4 is d to the 10 minus 4, which is d to the 6th. We can't simplify that one. Okay, so then we have this one, which is, now they're starting to combine and throw a few other rules at you. We've got, we could do this one 2 ways. Remember, 2 is 2 to the 1. Okay, so if I'm using my exponent rule, I can say, well, I have the same base. I'm going to subtract the exponents. So I'm going to get 2 to the 1 minus a negative 5, which is 2 to the 6th, which is 64. Okay, or I could do this one using what we just learned about negative exponents, which means 2 to the 5th is going to have to go upstairs. When it gets upstairs, it's going to multiply by 2 to the 1 and become 2 to the 6 again. So I can usually do these more than one way. All right, so here I have a z base and a z base. I'm going to subtract the exponents and get a z to the 2 minus 5 is negative 3. But we know that z to the negative 3 should go downstairs and become 1 over z cubed. And z cubed is 27. And 8 squared is 64. And 27 over 64 is the answer. So now we have 2 more complicated problems that kind of throw everything together. And we're going to deal with these in parts. Okay, so we've got 42 over 54 is my constant. I've got some r squared. I've got some r's here. And I've got some t's here. So I'm going to deal with the 3 parts of the problem separately. So 42 and 54, let's see, 42, if I just divide by 2, I'll get a 21, and a 54 divided by 2 is a 27, okay? And 27 is going to be 3 times 3 times 3, so 3 times 7, 3 times 7, and 3 times 9 is going to reduce to 7 ninths. So 7 ninths is our fraction. And then I've got r's. So I'm going to divide like bases, which means I'm going to subtract their exponents. And I'm going to wind up with an r to the negative 6 minus a negative 2. But negative 6 minus a negative 2 is a negative 4. And an r to the negative 4 should go downstairs and become an r to the 4 downstairs. And then here with the t's, I've got a t and a t. So I'm going to divide and subtract the exponents and get a t to the 7, which will go upstairs. So this should be my final answer when I do all of my little steps. And our last problem for this video is right here. Okay, so we're going to again take care of our 30 and our 48. I know they both divide by 6, so we're going to get a 5. Divide by 6, we get 5. Divide by 6, we get 8. And what's going to happen when we divide our k's, we subtract the exponents, we get k to the negative 2, meaning it needs to go downstairs and become a k to the 2. And then we end up with a b to the negative 6 over a b to the 4, which means a negative 6 minus 4, or a b to the negative 10 upstairs, which needs to be moved downstairs and become a b to the 10 downstairs. So we end up with 5 over all of that. And you can see if we just took this b to the -6 and moved it down to start with, that we would have a b to the 4 and a b to the 6 side by side, which would be a b to the 10 on the bottom. And that is the end of 6.1, and this is Mrs. A, and may God bless your day.